Hello, everyone. Welcome to this Project Portfolio Lab. And I want to welcome each and every one of you that has taken out the time to do that, even as we are closing out for the year. But before we do that, please do well to nudge your community member, do well to nudge your squad mate, your peers to join in for the first machine learning track project portfolio lab on regression. And yes, there will be a recording of this session too if they miss out on this live session. But do well to nudge them, do well to, you know, nudge them a bit, right? So yeah, you meet your host, I'm an product program delivery intern, and we have here with us Bali Jempi, our data scientist and technical mentor. Welcome, Abdul from Egypt. So let's be reminded of our rules of engagement. If you got any questions, we'll put them on the Q&A section. Feel free to use the chat feature liberally and respectfully. Listen, learn, and engage, guys. So yeah, over to the main session, which will be handled by Mbali. So over to you, Mbali.
Thank you, Aniviet. Hi everyone. So welcome to our first, regression webinar, where today we'll be covering our simple linear regression, right? So up until now, we've been working with data, we've been analyzing our data. We've been drawing insights from our data, but the most important part is that we can use data to basically give us or predict, right? This is where we then introduce our regression module, right? We are now going to be using data to predict future outcomes or future target variables, of which is something that we'll be talking about. So up until now, it has all about being understanding the data, working with the data, drawing insights from what we have. So moving forward, it's going to be like, okay, now I know enough about my data. I know what I'm working with, but I'm pretty sure with what I have, I can predict. But before we hop on to the technical part, just a quick icebreaker. Where will you guys be spending your holidays today? Right, so just quickly in the chat, do share where you guys will be spending your holidays. I think I'll be going for vacation for first time in a long time. But yeah. Anyone wants to share where they'll be going for vacation, spending it with family, or still just chilling, Netflix, nothing new, just an ordinary day before, we close off, staying at home, work, work, work. Oh, sorry. As for the work, work, work. Staying at home, visiting family. Oh, that's nice. I'm such a family person. I think it has its drama, but yeah, definitely the best people to be spending the holidays with. Probably travel home. Okay, that's nice. So I'm assuming you've moved, I don't know for what intentions, but yeah. But going to mom tomorrow, now working. Say hi to mom. Abir, I think that's how you pronounce your name. Resting at home. If any of my colleagues would tell you is that I am one person who will advocate for resting. It's the best thing, that has been given to us. So sleep, 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 rest, 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 binge watch a series, and then we'll be back next year, hop on to doing hard things again. Right. So again, as stated, today's webinar will be basically to help you guys understand simple linear regression. I do hope, even though you haven't covered the content on Athena, I do hope that you guys at the end of this webinar have some sort of an understanding of what simple linear regression is. All right, so we're going to quickly hop onto a demo. So these slides will be shared with you. Once you click on this link, it's going to take you to a folder. All right, and this folder has okay, need to make sure I edit that link. Okay, yes, this folder has all the resources that you'll need and that we will be working with in this webinar right now. So it will have the data set. These are just images that we'll be working with and that specific notebook. Okay. So again, the notebook will be shared with, the slides will be shared with you, and in the link, you'll be given all the resources that you will need. I just want to extend this guy here. Let me just quickly do that because I don't know why my screen is not fully shared. Apologies. Right, there we go. Okay, so again, what we'll be covering today is linear regression. So in the first part, we're quickly going to go through just the theoretical part and understanding how linear regression works, or regression, okay, specifically linear regression, because there's multiple regression models. But in this case, we will be covering your simple linear regression, all right? That will be having one input variable. Okay, so this lesson is designed for absolute beginners in data analysis or data science. It is structured so that it can be taught over multiple session lecture labs. Okay, that's just a note for you. The lesson structure will include linear regression, assumptions of linear regression, types of linear regression, model and training. This basically will be part of the practical part, our model evaluation matrix, and common pitfalls and mistakes when working with or designing a linear regression model. Right, so linear regression is a supervised machine learning algorithm. All right, so remember, in machine learning, we have supervised learning and unsupervised learning. So in the chat, who can tell me what the difference is? Right, quick, probably 3 words, 2 words. So what is the difference between your supervised machine learning and your unsupervised machine learning? Does anyone know? Right, so I do like having my lectures supervised learning. I know what I'm categorizing into, yes, and unsupervised learning, Solara, and unsupervised learning. Right, so I really would like for you guys to engage. I'm one person who loves having an engaging audience. Unsupervised learning, the model figures out the similarity and groups it. All right, correct. Simple terms, supervised learning, we have labeled features, whereas unsupervised, we have unlabeled features. So in supervised learning, it's sort of like, as it states in machine learning, with supervised learning, it is I teach you, I give you a guide on this is what will be in the exam. This is what you will have to study. These are the sections that are given. All right. I am guiding you. I am supervising on what to study, what not to study, and then there'll be an output of which hopefully will be for you to pass. All right. Whereas with unsupervised learning, it's basically you just winging it. So just basically reading a random book. You take a book out of the library, you read, and from what you have learned, you can then classify. Maybe now you want to change the lifestyle that you want to live or whatever you are eating. That is sort of the difference of supervised and unsupervised learning. We are teaching the machine by supervising over it on what to input and what the expected output is. Whereas with unsupervised, the machine does not know the expected output, so it basically categorizes whatever it takes in on its own. Okay, so again, linear regression is a supervised machine learning algorithm used to predict a numerical value, right? So in predictions, there are many predictions that we will have or models that we will have throughout the machine learning track. With linear regression, this is us predicting numerical values, right? Sometimes you could predict whether or not someone may pass or fail. In that case, we could use what they call a logistic regression model. But in this case, because we want to work, or we are working with numerical values, we will be then using a linear regression model. The one thing about linear regression model is that you want to make sure you understand the relationship between the variables, right? So you're given variables, or the data has specific features and variables. So as you look at it, as you understand your data, from what we have learned up until now, you draw up those statistics, you work out the correlation and so forth, and you want to understand the relationship that you're working with these different variables. So example questions that linear regression can answer is, how does study time affect exam score, right? So suppose you are given a data set of students, time that they have studied, and their exam scores. You would take that data in, you analyze it with whatever methods that you would want. And from there on, you can draw up a relationship. The one important thing when working with linear regression is that you want to make sure that the relationship between those variables are linear. Okay. Another example is how advertising spend affects sales. Okay, so for instance, you have given those sales and advertising costs, and you notice that as we spend more on advertising, our sales increase. In that case, we could say, okay, what could possibly happen in the next month if we spend 300 more than we did in the last month? Would that increase our sales? That's when we decide from the past data that, okay, I'm going to now build or use linear regression to help me predict whether or not if I increase my advertising sales by 300, whether my advertising costs by 300, whether it will increase my sales. Last example would be, how does house size affect house price? If the house is bigger, does it affect the house price? All right, so same procedure, understand the relationship between the two variables, and once you have discovered whether that relationship is linear, then we can use linear regression to then predict future values. Okay, so at its core, linear regression fits a straight line through data points. All right, so again, remember I did state that we need to make sure that those variables that you're working with have a linear relationship. That's why you then have a linear regression model that predicts a value based on a linear relationship between an input and an output variable. So for real world intuition, suppose you have an image plotting x-axis of our studies. So this is basically this example, and y-axis of example marks. You will likely notice that as hours studied increase, marks also increase. Linear regression then finds the best possible straight line that represents this relationship. I think there is an image here below that will show you on how that basically looks like. The main goal is to use the line to predict future outcomes and quantify relationships. So with linear regression or with any predictive model, it's never always 100% accurate, all right? That's why we have errors, which then we use our evaluation matrix based on our errors to see how big our errors are, how small our errors are. What we want to make sure is that we minimize our errors, all right? So note, a model will never perfectly predict any specific output value, all right? So it is a model, it is a machine learning, it's understanding from the data. There are other forces that may be affecting some of the values that we have, but we do assume that we have given the machine enough data to test and train and understand how these variables work hand in hand together for it to actually predict those specific values. Okay, so simple linear regression equation looks like that, right? I'm sure you guys are very familiar with it. It's basically your line equation. So remember, it fits or finds the best possible straight line that represents the relationship between these two variables. So what are these two variables that we're talking about? We have our target variable. So this is the guy that we want to predict. Which one is this one? This is our exam marks. We are predicting whether you will get 80, 60, 100 based on an input feature, which would be the hours that you have studied, all right? So we want to predict, let's say we are building up a program. And in a program, we build a study guide, and in that study guide, we want to recommend the number of hours to students to study for them to at least pass the module. This is some of the models that will help us give those insights, right? And be like, okay, the model shows that on average, if a student studies 8 hours in, or let's say 10 hours in a week for the specific model, most of them have passed. Draw up that prediction model and decide whether or not we're going to have a threshold or draw insights and build up that study guide. We have a slope, which basically shows us how much y changes when n increases by 1, right? Obviously not taking into account, for example, that the intercept. For example, if I have m is equal to 1.5, then if I increase x or my hours by 1, then my score will increase by 1.5%. Okay, you guys remember what gradient is? It is our rate of change, right? So basically, at what rate does my target variable change based on my input variable? All right. So remember with correlation, do you guys remember what correlation is? It's in the chats. Who can tell me what the Pearson correlation does or tells us? All right. What can the Pearson correlation variable tell us? Relationship relationship between variables, the association. Yes, the association between variables. All right. Yes. The strength of the relationship. Yes, but there is this one specific word that I'm looking for that you guys haven't used yet. Right? So we are working with the relationship, but there's one very important the strength. Nope, not the direction. So Pearson relationship tells us the linear relationship between variables, right? So sometimes your variables may have a relationship, but it may not be linear. That's the one limitation of our Pearson correlation coefficient, is that it only measures the linear relationship between variables, right? It ranges from -1 to 1, whereas if you're closer to -1, it tells you have a strong negative correlation, meaning if this guy increases, that guy might decrease. All right. So if, let's see, I'm trying to find your level of petrol or gas in your car. If you increase the speed, the level of petrol will decrease, right? That's the type of relationship. If our correlation coefficient reads that from these two variables, it is closer to -1. If it's closer to 1, then it has a positive linear relationship, meaning as I increase, you increase. As x increases, y increases. Negative, as x increases, y decreases. All right. So that's what the Pearson correlation coefficient, just as a quick what do you call revision for you guys to remember, right? Because it is very important. We are going to do it in the practical as well. Okay, so that guide tells us that specific relationship that we are working with within our data. So assumptions of our linear relationship. Okay. Linear relationship works best when the following assumptions hold. Linearity. So this is basically why the Pearson correlation is very important. The relationship has to be linear. A change in an input variable causes a proportional and consistent change in the output. So note, the reason I was talking about correlation is because M in our linear regression tells us exactly how much that proportion of change is to our target variable based on our input variable. Our Pearson correlation coefficient tells us the strength of the linear relationship. All right. So that's 0.8 tells us that we have a strong positive linear relationship between x and y. But if m is equal to 0.8, it means that if I increase x by 1, then I will increase x by 0, y by 0.8. Pearson correlation tells me how strong the relationship is. Like, yes, this is strong. You can build a linear regression model based on these two variables, with the output variable being y and the input variable being x. Cool. So when you plot the data, okay, so what type of graph would you use to check the trend of your data? I feel like I'm now doing revision with you guys. What type of graph would you plot to see the trend of your data or to spot that relationship, right? So remember, if we want to see the distribution of our data, we would use a histogram. If I want to see the trend of how my data moves, what graph would I use? A scatter plot. Great. Perfect. A scatter plot. A scatter plot will tell me how or what trend that data has, all right? Okay, once you can identify that that trend is moving upwards or there's some sort of trend either straight upwards or down, right? That could be either negative Pearson correlation coefficient or positive Pearson correlation coefficient, all right? Cool. So sometimes when you are drawing up or plotting this data in a scatter plot, you may not see those trends, or it's something that we will see. All right. If that happens, then what will we do is that we will then use our Pearson correlation coefficient to see whether or not there is a trend. Right. So again, the first assumption is that we want to make sure that there is a linear relationship. So this guy is what we would ideally like to see if we draw up a scatter plot from our input data and our output data or target variable. We then draw up a linear regression line, that is our line of best fit, that basically is predicting all these points. So this guy is predicting for this point. Here is predicting for that point, not exactly on the point. There is a slight error, and so forth. This guy is predicting for this point, and that distance there is our residual or our error. All right, cool. Another assumption is independence, right? Observations are independent. So all these guys are independent. This guy being here is not affected because this guy is there. Each point should not influence the other. One observation should not depend on a previous or nearby one. Then errors should not be correlated. The one thing that we want to be correlated is our input and output variable, right? We want to see that correlation and see them move in a specific point. But our errors should not be correlated. We don't want to see those points is that because error 1 was high, error 2 will be high, error 3, and so forth. All right. Then we have what we call homoscedasticity. English. Homoscedasticity, right? Which means constant variance of errors. What this means is that the spread of residuals, again, or errors, should be roughly the same at all values of x points. Okay, so basically, what we want is there should be some sort of not equal, right? We don't want our errors to be equal, but we want them to be somewhat evenly spread, right? So we don't want, you see here, the errors aren't or sort of the same distance. Once you find errors there and errors there and errors there, that line is not the line of best fit, or our variables do not have a linear relationship. So we shouldn't be using a linear regression model to try and predict our target variable, right? So as we can see, this line is somewhat in the middle of our data points, right? So those errors, the distance are somewhat evenly spread. We don't see another point there or 10 other points here and 5 other points there. They are evenly spread, okay? So in simple terms, the model should be equally wrong across all predictions. The spread of residuals refers to how wide or narrow the errors are. If the residuals stay equally scattered everywhere, that is a good line of best fit, and become more scattered in some regions, then we have a problem. As I stated, you see that line sort of like in the middle of our data. If there was more data here and less data there, then we know that, okay, no, that line is not the one. Then with regards to our errors, we want normality. Okay, so we want the errors to basically have that bell shape, the normal distribution. Okay, and what graph, I feel like I just mentioned it already. What graph would we use to see whether our errors are bell-shaped or normally distributed or follow normality? Okay, so you guys remember the normal distribution? Remember it has that bell-shaped curve, sort of like yeah, a bell. An upside down bell. Histogram. All right, correct. We would then draw up a histogram to basically see whether our areas are normally distributed. So we want to make sure that this is what our areas look like when we have then created our model, right? We want to make sure that the areas are distributed in that manner. Okay, cool. So we have assumed that we have a linear relationship. Once we have drawn up that line of best fit, we see that there's homoscedasticity. We see that there's normality of errors, but that's not enough, right? And that's why we then have evaluation matrix where we have our R squared, our mean absolute error, and our mean squared error, and our root mean squared error, right? So hopefully, if probably I don't cover it too much, there is definitions and formulas in the content, but R squared measures how much variance is explained from our input data to the output data. Okay, so what does that mean? The variance or the changes in X, let's say our R squared is 0.8. This means that 80% of the variance in my target variable is explained in my input variable. All right, so those changes that we see in our exam marks, 80% of which those changes from student 1 to student 2 or student 3, student 4, student 5, that change 80% of it can be explained from the number of hours of each student that they have spent studying for the specific exam. All right. So that's what our R squared means. It ranges from 0 to 1, and you want it obviously to be quite high, right? So when you have a high R squared, then you know that, okay, I'm working with the correct variables, right? So these variables, my X value basically tells or does help in or has a huge effect on what's happening with my output variable. Then we have our mean absolute error, which is basically your actual value minus your predicted value all squared, and that is the average. So divided by the number of observation, that gives you the average. The reason this is not the most ideal uh, is because it's not it's squared, right? So it doesn't use the original data scale, right? So we've now squared our value. So it's very hard to interpret your mean absolute error, but we do want it to be as low as possible. We then have our mean squared error and our root mean squared error, which basically these ones as well, if you want to find the formulas, you can check on the content. It penalizes large errors more heavily, all right? So if, for instance, here we have a point there and we have a point there, then that guy, which one is it? Oh, where are we? Mean squared error at most will penalize more than your root mean squared error. Don't know why. Anyway, all right. Okay, so these are our evaluation matrix. We want these guys to be, okay, these three guys to be as low as possible, but you want your R squared to be as high as possible. Okay, so we understand theoretically what linear regression is, what we need to do, what assumptions we need to have, and what we need to do to check what is happening. Okay, now let's hop on to the practical side of our linear regression lecture. All right, so we're going to be working with a data set. It is student performance, right? So those columns will include the number of hours they studied, which ranges between 1 and 9 hours. You have its attendance percentage, which ranges between 40 and 50 and 100%. We also have previous test scores, which ranges between 40 and 90, the sleep hours that ranges between 4 and 8 hours, and final exam score, which is basically our numerical target. Okay, so we will obviously be given that data or those values of our final exam score for each of these 150 students, and then we're going to build a model to see whether or not we can actually predict. Libraries that we will be using are your pandas, your NumPy, your matplotlib, since we're going to be plotting data as well, your seaborn for your scatter plots. You have then our sklearn model selection. Okay, so once you build a model, right, remember we're going to be given a data set, all right? So if we're going to train a machine to learn something, we need to give it something, right? Just as you as students. We'll give you the content, we give you the assessments, we give you these webinars, right? We're training you. We're training you to understand what machine learning is, what Python, what statistics, and so forth is, right? Then at the end of everything, we test you, right? And that test is probably what, 3 hours, 4 hours, or how many ever hours an exam would take, right? So that's the same thing that we do in a machine. We give them so much for it to learn, and we leave so little or so much for it to then test whether it understands. So in the train test split, we have a data set. The most common split is 80, your 80% training data, 20% testing data. So it takes 80% of that data with no order, doesn't take like the first 120 and the last 30 data. It randomly selects 80% of the data, right? That basically still contains the same distribution or the same patterns as it would have as the whole data set, all right? So it splits and takes 80% of the data for training. This is the what? This is your assignments. This is your short quizzes. This is the content that we provide you, the webinars. Then we're going to take the 20% to test. Okay, now that I've used that data and I've learned and I've understood how the patterns work and all the relationships and so forth, then I am going to take this 20% to see if I can predict each of those data points. All right, so that's what the train test split is used for. We then call that linear model, which is your linear regression, basically to fit that line of best fit in our data set. Then our matrix, basically our evaluation matrix to see our mean absolute error, mean squared error, and root, root, R squared score. Okay, first things first, we're going to load our data set. Haven't run my libraries. Okay, let's give that a moment. Cool. So we run that, we load that data set. Remember that the file or the folder that is in the link of the slides will give you everything. So you want to make sure that you download that whole folder and everything is in the same directory so that the code basically runs and you don't have to change the paths and so forth. Right, so we see that we have hours studied, attendance percentage, previous test scores, sleep hours, and final exam score. Then we want to understand our data, right? So understanding our data is that we want to see if we have any number of variables, if there are any rows with any null values, any statistics as well that we can have, your mean, your average of your numerical columns, right? So if we run that, we see that for the non-null or number of null values in each of our columns, we have 150 non-null values. So we have no null values given that we have 150 entries. And if it says of those 150, 150 are non-null, right? We see that the hours studied are integers. Attendance percentage is also an integer. Previous test score is an integer. Sleep hours an integer. And final exam score is a float. Right. We'll also have then our summary statistics, where we have the count, the mean, the standard deviation, the minimum, the first quartile, second quartile, third quartile, and our maximum, right? You read through that, you see that the average hours that a student studies was 5.3. The average attendance percentage was 74.29. We have previous test score average being 66.25, sleep hours being 6.04, and final exam score being 81.89. That's quite a high average. Okay, this class is doing well. Right. So as much as we are reading, the model is basically going to do the same as well, right? We're just looking like, oh, okay, we see minimum, just to understand what we're working with, right? Then just for what convenience, you always want to make sure that you check if there are any missing values. So then we would use that is null function, even though we know that we don't have any null values, and we sum them just to see the amount of null values that we have. And in each column we see that we have 0, 0, 0, 0, which basically confirms that info function that we have there. All right, cool. Then we draw up our scatter plots. Why do we do that? Because now we are starting to analyze our variables. Which one between our target variable, right? Remember what our target variable is, final exam score. All right. So we then decide, okay, cool. Now I want to see how each of these variables act towards or with the final exam score. All right. And as remember I stated, you want to see the trend first, right? It'd be easier as just see like, okay, no, I see if that this has a trend, right? With that target variable. So if we run that, we have multiple scatter plots that basically describe each trend with regards to our final exam score. Okay, so as you can see, we have used the for loop to basically run through every feature in comparison to our final exam score. So that's what this for loop is doing here. Runs does our studied, runs does attendance percentage, runs does previous test score by final exam, sleep hours by final exam. Okay, so that's why we have that for loop. Remember, a loop runs through every element and performs this, goes to the next element and performs that. And that's why we have multiple scatter plots. Right. So if we're looking at those scatter plots, we see, I don't know about you, but I'm the reading is not reading, right? I'm trying to look linear. Okay, there's something happening here. But would I say it's a linear? Maybe. We're not sure. All right. If we look at our attendance percentage versus final exam score, we're looking, if we put a line there, yeah, they would be evenly separated, right? But would it be ideal to use a linear relationship? We have our previous test score versus final exam score. Same, may look like there's a linear relationship, sort of does, honestly, but can't just trust my eyes. We have the tools that can help us identify these trends that maybe we cannot see in the naked eye. So, who can tell me what do we need to do next? Uh, at Adamu, the data set will be shared with you in the folder. Right, so when you click in the link in the slides, you'll get the data set and everything, basically. So who can tell me that now that we've looked at our scatter plot, and we're not really sure which one has a linear relationship, right? What can we do next? Draw the line of best fit? Not yet. No. What can we do? We're looking at the data and we're like, okay, I'm not sure if these people have a linear relationship. So what can I do next? What can I do next to see, well, what's happening? Can we do with bar? No. We just went through it now. If I look at a scatter plot and it doesn't work, how else can I see whether variables have a linear relationship? Now, well, remember a histogram So remember, scatter plot is to see the trend of my data, right? And we tried that. It's not working. Now I want to see whether my variables have a linear relationship. Linear relationship. What did we discuss on what can help us identify whether variables have a linear relationship? Use the equation? No. So the equation is literally the loss pot. Pearson correlation. All right, right. That's right, Christine. We have plotted and have tried to identify a trend between the two variables to see if there's an upward linear trend or downward linear trend. And we don't see that. Okay, so the next thing that we want to do is we're going to use correlation. Remember, we're working with linear regression. We want to make sure before we even jump into using the equation, right? We want to make sure that we have our variables have a linear relationship. That's the first part before you even jump into the equation, before you even fit that line of best fit. How can I have a line of best fit if I don't even know whether or understand whether there is a linear or a line that can even be fit? All right. So first things first, scatter plot. Scatter plot, if you can see, if we could explicitly see something that looked like that, we could have said, okay, no, I'm confident enough that there is a linear relationship here. All right. But we don't see something that looks explicitly like that. There's something that looks like it's happening here, but we're not sure. All right. As well as here. But still, we want to find the one that we are strongly confident about that has a linear relationship. So we've looked at the trend of our variables using a scatter plot, and it didn't work. Our next best thing is our Pearson correlation. This guy is going to tell us explicitly that, listen, the two variables have a linear relationship or they don't have a linear relationship. And this is when we introduce our correlation heat map. So we're going to use our Seaborn library where we draw a heat map where we call our correlation coefficient, right, using the cor function. So this guy here calls the data frame. So remember, we saved this data as df. Okay, when we imported it, we saved it as df, right? So we are saying, or this function basically says, where are we? Here. This function basically says, from this data frame, for each variable, draw up a correlation coefficient. Okay. The heat map, Solara, the heat map basically shows us how strong the correlation is. Okay. So it's still a Pearson's correlation. We're basically showing a heat map to show the strength of the correlation. You'll see once I run it, and I hope it makes sense. So if we run that, we see that the darker the block is, the stronger the correlation. That means the Pearson correlation. So we still are, the values here are values of our Pearson correlation. All right. So see, not the darker, man. Sorry, the lighter. So the darker it is, the lower or the weaker the relationship between those variables. Whereas as we get lighter or get closer to here, the stronger the relationship is. So do you understand how that heat map is working, Solara? Right? If we are dark, the relationship is not so strong. We're closer to zero. If we are lighter, the relationship is strong. We're closer to one. So ideally, the colors that we would want is somewhere around that orange colors there. Does it make sense? All right, yes. So we still are working with the Pearson's correlation. These values here are your Pearson correlation coefficient. Okay, so if we look, who's quite light, right? So we have 1, 1, 1, 1, 1. And the reason we have 1, 1, 1 is because the relationship between its own and a variable and itself is always perfect. If ours studied are increased, then you're right, ours studied are increased. Okay, so that's why it has a perfect linear relationship. So if you draw hours by hours, you'll have a straight line. Okay, cool. So we see 0.77. So this is the guy that we're looking at. We look at hours studied and percent. Let's look at final exam scores, given that that's our target variable. We look at final exam score and hours studied, and we have 0.77. We look at final exam score and attendance percentage, and we have 0.25. Previous test score, we have 0.4. Sleep hours, we have 0.05. And obviously, with itself, it will have a perfect relationship. But now the thing is, we don't need these clearly, right? These guys don't give us a strong linear relationship between that specific variable and final exam score. Okay. So we notice that hours studied is quite high. It's greater than 0.5. So that's quite a strong positive linear relationship. Who can tell me or who can interpret this Pearson correlation value? What does this mean? If remember, don't confuse it for R squared. This is your Pearson correlation, which is like a small r, right? The mathematical, what is it, notation for it is a small r. So I'm not asking about your R squared. I am asking what or how can you interpret the 0.77? Attendance percentage against attendance percentage like that. So yes, Solara, only hours studied is correlated or strongly correlated. Yes. Positive correlation between hours studied and exam score. Haruna, yes. The more hours, perfect. The more hours a student studies, the higher the exam score will be. That is correct, Kennedy. So that tells us that this guy highly affects this guy here, right? So as Kennedy stated, the more hours that I spend studying, the higher my final exam score will be. All right. So this basically is a positive, strong, linear relationship between hours studied and final exam score. It is very important that you have positive, strong, and linear relationship. Okay, those three terms are very important, okay? Because correlation measures the linear relationship. It has to be strong for us to even state that it's a linear relationship. What else did I say? Positive, linear, and strong, okay? And again, it has to be a linear relationship for us to even think of drawing up a linear regression model. Positive, strong, linear, right? That is correct. Obviously, it's not, this is just based on the context of this correlation coefficient value. But if it was negative, obviously, it would be negative, strong, linear. So you want to direction, strength, and linearity. Okay, so when you ever, not only if you're asked in a question or in an MCQ in our content, just in general, suppose you do another course, I hope you will remember these three important terms: the direction, whether it's positive or negative, the strength, whether it's strong or weak, and the linearity. All right. It has a positive, strong linear relationship. Had we had no coefficients and stated that, listen, I can't draw up a linear regression with this data set because why? I have a weak positive non-linear or positive linear relationship, right? Meaning that I cannot explicitly say that this relationship is linear. One, it is positive, yes, but it is weak. And therefore, my linearity is sort of ambiguous at this point. And I'm not sure if I can give you a linear regression model. Okay. Attendance percentage against final exam will now be positive weak linear relationship, I believe. Yes, it is a positively weak linear relationship. Okay, so the linear relationship is weak, and therefore I cannot draw up a linear regression model using the specific variable as an input variable for my output variable final exam score. All right. Cool. Then again, data cleaning. This is basically part of the understanding the data. We will fill missing values using the median. Who can tell me, Faith? I swear this is the last question, maybe not the last question, but very important. Who can tell me why it is ideal to fill your missing values with a median instead of a mean? Outliers. Perfect, right? That's correct. Outliers. Median takes in consideration our outliers. All right. Yes. So we're going to fill in our missing values with our median. But then, of course, we didn't have any missing values. So we'll just run that for convenience sake. Then we've selected our feature. So we've identified who has a linear relationship. What do you think about the statement when experts are talking a discovery or experiment, correlation does not mean causation? That is correct. Correlation does not mean causation. Me studying for hours does not mean, for instance, if I study 10 hours, but I don't understand the work, right? It does not cause me to pass the exam. It does state that um it has an effect, but it does not cause you to pass your final exam. It is not the result of you passing the exam. Someone can spend 15 hours and someone can spend 5 hours. But the person who spent 15 hours could fail, and the person who spent 5 hours could pass. All right. So correlation does not mean causation, as well as there's also something with that is also referred to as a spurious correlation. Okay, if you've also heard of that, that means when there is a correlation between two variables that does not make sense. Okay, so what does that mean? For instance, suppose you have number of people who drowned and ice cream sales, and you check the correlation between these two variables, right? You realize that they have a linear correlation, right? As there are high number of drowns and high number of ice cream sales. But the reason that these two look like they have a linear relationship is because there is another variable, Z, let's say, or third variable, that we're not taking into consideration, such as temperature. All right. So if it's a hot day, a lot of people are swimming. If it's a hot day, a lot of people are buying ice cream. Okay. That will cause an increased amount of people who have drowned because a lot of people have were swimming on that day. Also increase the amount of ice cream sales because it's hot and a lot of people have um bought ice cream. One could assume that yes, people drowned because there was a high increase on ice cream. It doesn't make sense. That's why there also needs to be a human analysis behind everything that you do and all this data and analysis that you are doing. We still need that gets common sense, right? To be like, no, man, obviously there is some other factor affecting one, two, three, four. Ruth, I hope I'm making sense as to what it means where correlation does not mean causation. All right. So just because someone studied 10 hours, it doesn't cause them, or it's not the cause of them actually getting that final exam score, but it does have some sort of, you know, effect. Okay, or some sort of association. I mean, like if two people didn't study at all and didn't attend and basically don't know the content, then obviously they're going to fail. Not because they spent 0 hours studying, but because they just didn't bother. They don't know what's happening. All right. Doesn't imply causation. Some of the matrix that can check causation is your chi-square test, I think. They'll probably look into that as well. Cool. So we have identified our features and we've realized, okay, there's a linear relationship between our studied and final exam score. We then create a split, right? Remember what I had mentioned about training a machine? You need to give it something to actually learn and then test it on something that will see whether it is working. Each of these parts of dataset that have been separated into two share the same distribution as the normal data set. All right. So we have our X train, X test, Y train, Y test. Our X train being, we will find the notebook along with the recording. Yes, that is correct. So X train, X test, that is the X or hours studied for our training data, and that is our X for hours studied in our testing data. As well as Y train and Y test, it is our Y or target variable in our final exam score, and it is our Y in our test or target. It is our target variable in our testing data set. Okay. We are splitting it into 80-20. So 80% of the data that has been randomly selected will be used to train the model, and 20% of the data will be used to test the model. That random state 42 is so that we use the same data, that first 80 and that first 20. Because if we don't have that random state, it's going to again randomly select another 80% of the data, randomly select another 80% of that data. So we don't want that. We want to make sure that we are consistent in what we are doing. Right. So we run that. We then call that linear regression model. We've basically decided that, okay, cool. I have my features. I know these two have a linear relationship. I'm going to train my model using 80% and 20% for test, and I'm going to fit this to my linear regression function. So we call that linear regression function, and we fit our X train and Y train. We run that. Then we can draw up our coefficient, right, to basically interpret how much that X value affects my Y value. Remember, so this is basically our M, that gradient value, okay? Remember, I stated that that guy tells you the exact proportion of how much my Y is going to change given that my X changed. So if we run that, we see our M is equal to 4.2. So if I change X by 1, or if I change the number of hours by 1, then it will increase my exam score by 4.24%. Okay, interpretation example. If hours studied has a coefficient of 4.5, then the extra hours studied increases the predicted exam score by 4.5 marks. Assume other variables stay constant. All right. So now let's make those predictions and use our X test to see our Y predictions. And we see that our Y predictions have then been done on that 20% data set. Then we run our model evaluation. So note that this guy, our predictions. All right. See if we can look at them alongside our Y test. There. Okay. Oh, how long is that? Wish it was in data set form. I mean list form, so we can identify them individually. Jeez. So this is our Y test score. All right. This is our X. Remember, our Y predictor or target variable was a float, right? And our X variable were integers. So this guy here gives us our Y values. I'm not sure, but it should be, given that we use our X test. Okay, so for the first one, we predicted 82. No, we predicted 93, and it was 82. 75, and it was 68. 52, and it was 72. 64, and it was 65, so forth and so forth, right? So these are the actual values, and these are the predicted. Okay, so I'm going to leave that as Y test. So that once you think, right, cool. Then we do that model evaluation where we have our mean absolute error, mean squared error, root mean squared error, and our R squared score. So R squared wouldn't necessarily say it's that high. All right, it's okay for an R squared score. That means what? Okay, I think this may be my last question. Who can tell me what does that R squared score then tell us? Nope. Anybody? What does that R squared score tell us? This guy's gonna give us an error here. So our R squared score is 0.51. No, remember, R squared is not your Pearson correlation. Pearson correlation has, so let's say, print, what was our Pearson correlation? Or what was our Pearson correlation? I think it was 0.77. Okay, so our Pearson correlation is R. Let me say Pearson correlation was 0.50% of the final exam score can be explained by what? Lucy, you're on the right track. 50% are about variation in final score can be explained by studied hours. That is correct. 51% of the variation or the changes in my final exam score can be basically explained by what's happening in my studied hours or a number of hours that I have studied. All right. Then we run our residuals. Remember, we wanted our residuals or our errors to have normality. So we're going to run that. Okay. Oh, that was supposed to be. Okay, the residuals aren't that great. Okay, we do want them. So this is basically checking the homoscedasticity. All right. So we would have ideally liked them to be sort of distributed. Remember, we want them to have a somewhat even spread, right? So we see our errors are running left and right, and some are too far. We would have ideally liked them to be centered around the specific line here. So yes, homoscedasticity. Hopefully I'm pronouncing that right. Yes, that is correct. But now there's not much homoscedasticity. So this model, not well fit, right? Our R squared score is 0.51. Okay. The only thing that we can confidently say is that those two have a linear relationship. But with regards to our linear regression model, I wouldn't necessarily say this is a good one. All right. So then let's try and predict for a new student. This is probably going to give me, oh, there we go. So if a student has hours studied being 6, okay, and we want to then predict a score, then predicted final exam score would be 85.29. All right. Cool. So we have come to the end of our simple linear regression. A very interesting one. So next section is that we'll be going into our multiple linear regression. All right. So now remember that we had hours studied, right? We had hours studied, but we have multiple features. For example, if we had this guy here being 0.8 and this guy being 0.9 and so forth and so forth, we would have used all those multiple features to basically draw up a multiple linear regression model. And what that looks like is that it doesn't now have, where's that equation? Ugh. Right? We don't have now one input variable, we have multiple input variable. We will also have multiple coefficients because why? This guy here, or these coefficients, give us the proportion of how much it affects our target variable. So we would have, let's say, B1 or beta 1. Okay, that's like horrible, but again, once we jump into that multiple linear, we'll see how it works. B2 for x2 plus B3 for x3 and so forth with whatever number up until our basic intercept as well. We just say B0. All right. So that will be your multiple linear relationship, of which is something that we'll discuss in our next webinar. So do go through this. It's almost the same, just a couple of other things that we'll be covering, such as your multi-collinearity as well, to make you understand that some of these variables mustn't have any relationship amongst each other for us to then draw up a multiple linear regression model. Okay, so I hope you notebook will be shared. Thank you. Yes, interesting. Oh, you're welcome. So yes, this is just again simple linear regression. Note what to remember, what you need. You need to make sure there's linearity. That is the most important thing in a linear regression model. Before jumping into it, we want to hop on to understanding whether we have a linear relationship. We check scatter plot. Scatter plot doesn't work. Pearson correlation. Right, we have described that we have a linear relationship. We then hop on to building or fitting that model. Valuation matrix. Want to make sure our residuals are evenly spread. Homoscedasticity. I feel like I don't know how to pronounce your name. Adbert. Woo! Karu. I think that's your surname. Yes, when you shouted homoscedasticity. Right, that is correct. Those are some of the main things that you want to make sure you have covered. And most importantly, that was asked by Ruth. Correlation does not mean causation, and sometimes you may have a linear relationship between your variables, but that correlation may be spurious, meaning there is a third factor that is affecting this relationship. Very important. Common sense is also needed when we are working with data. All right, that's why ChatGPT won't take us out yet. Right, so let's quickly hop on to our Q&A. See if we have any questions. So one question, will we have this notebook used in the session? Yes, of course. So as I stated, once you click on this demo link, it's going to take you to the folder, right? It's going to take you to the folder of which will have everything. Okay, you want to download everything and put it in one folder. This is the notebook that we have been working with. These are just the images I have used. And this student performance data set is the data that I was using. This is also a PDF of basically what we have been going through in case maybe you want to look at it on your phone and you're in transit. Okay. Right. Where were we? Why did I move? There. Okay. See if there are any other questions. Yes, the notebook again will be shared that was used in this session. Hey, guys, have any questions? Let me check the chats. I'm sorry, but where is the demo link? Here. I'm not sure, have they shared these slides with you guys already? So once you select, when you click on demo here, it should take you to the folder. All right. Let me probably try to share it. Did I save it? No, I did not. Let me try and share that link in the chats. But I'm sure once you because I can't really copy it right now, but once you get the slides, just select this link and it will automatically take you to that specific file where you'll find everything. All right. So a poll has been launched. Please do respond as to whether or not you do understand at least how simple linear regression works. Linear, correlation, homoscedasticity. Like Ruth shouted that out, now it's in my head. And yes, the poll has been launched, so please do complete the poll. Thank you so much for you guys for coming. Let me see if there's another question there. Hello,
Thank
question,
you,
please.
Bali, for that
Oh,
question.
sorry, there's a question. Is there a session next week and active models? So I think Anipiet will be covering that on next steps. Okay, so please don't forget to complete the poll, and I'll see you guys next year. Thanks again for coming, and I'll hand over to Anipiet. Cheers.
Yes, thank you, Mbali, and we very, very, very hope to see you next year too. So yes, our learning and technical support, please let's remember we have Ask the ALX Data Programs team, and it is that space on the community where you can ask any program content related question. Please use this space only for this purpose. We also have Fresh Decks is your go-to space for all program support, and especially in this break period that we're entering. And we also have Answer Base, and it's a channel that is dedicated for you to ask and get answers to complex content questions. So with that said, let's remember on our assessment for this week is going to be due once we resume from the break. That will be on 6th January 2026. So you have a whole 2 weeks to complete your assessment, and also be informed that there will be an advanced content that will be released, which the assessments will also be due the following week. So thank you and happy holidays to you all. Do my screen or something.
Tena uzikumbuke ahadi zile ulizonigea, mapenzi vita wendo gadi, baby utanitetea, usiruhusu wadangaji wakaanza kukuzoea, unawajua mafisadi watapata cha kunisemea, akili itazunguka zunguka 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 itazunguka, kiniacha mwenzako, maana nitaumbuka umbuka umbuka umbuka, nitaumbuka yote kwa ajili yako. Kwe 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 nitalia, kwe kwe kiniachilia, kwe 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 nitalia, kwe somo unavyonipatia. Oh my God, oh, I'm crazy for you. 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 Rakata rakata rakata, rekete rekete rekete, rikiti rikiti rikiti, rukutu rukutu. Rakata rakata rakata, rekete rekete rekete, rikiti rikiti rikiti, rukutu rukutu. Rakata, rakata, rakata.